Okay, so it is already 2, so let us start today's lecture. So it's good that at least 70-80 students are already in campus. And when I conduct online classes, attendance are at 20-24. So I think offline class is better. At least on average, 50-60 students will attend, and I'll try my level best to record it for those who are not here. And the only problem is I'm recording it today. I'll check it. If the recording is not good, then the only problem may be this speaker as well as microphone. So maybe a good microphone who will not capture the background noise will be better. But I don't know. Maybe if you have any solution, you'll give. But let us try today's recorded video. Only another limitation is I'll not use this board because if I use this board, then it will not be recorded, right? So I'll try to use the whiteboard of the tab. So it's not a very good way to teach because sitting in a chair in offline classes are not a good way, and we don't like that. But anyway, we'll try to do this. I think one online attendance is also there. Okay. So I think you have studied the replacement policy that I have explained in last class, that is DIP. Today I will discuss another replacement policy that is called RRIP. So remember the short name. Maybe sometimes if you forgot the long title, you remember every paper with the short name. So here the title, you will remember this paper as RRIP. So this replacement policy is proposed in 2010, and it's a very popular replacement policy. Though you will find a very less difference between this replacement policy and DIP that I've explained in last class, but still, even most of the modern processors, Intel processor as well as AMD processor, they use this replacement policy for last level cache, RRIP. It has different versions. Maybe the version that they are using for their processors maybe exactly not may not be same, but still some variant of RRIP is used in processors also. Though there are many recent replacement policies also exist. In next week, one of my PhD students will explain you two very recent replacement policies based on learning techniques. So one is called Hawkeye, another is called Mockingjay. So Mockingjay is just published in this year. But after explaining this paper, I'll not explain any more replacement policies paper. Then from next week, I'll start explaining another very important concept of cache memory. It's called cache coherence. So if you go to the textbook, a very small section is given for cache coherence, but I think cache coherence is very important section. So what I'll do this week as well as next week, I'll not go to the textbook again. So for this 2 week, you have to follow whatever additional material I'm providing, and maybe from after the next week, again we'll go back to the textbook and we'll follow the next chapter. So because cache coherence that I'll explain next week, you will hardly find any good book for this. So if you have to depend on some web pages, and also main source of understanding cache coherence will be my lectures. And since I'll not prepare my slides, so you just listen my lectures. I'll record those lectures also. And even if I don't record them, also it's not a problem because I have already recorded videos for cache coherence. So I'll teach here as well as I share my recorded videos. So watch those lecture videos. And if you face any problem to understanding cache coherence, then let me know. These things are easy, but cache coherence is complicated. But you should know what is called cache coherence. It is very important. Okay, so when we'll start today's lecture, let me quickly revise the concept that we have studied in DIP. So we have studied DIP is a combination of LRU plus BIP. And then if I extend BIP again, then it's a combination of LRU insertion policy, right? Plus MRU insertion policy. Means BIP means with high probability it insert in
हाँ. ओह, बहुत कुछ है, कुछ ना कुछ तो भूल जाएंगे. Okay, now it is shared. Okay, so DIP is a combination of LRU plus BIP. And what is BIP? BIP is a combination of LIP and MIP. LRU means insertion at LRU position, and MIP means insertion at MRU position. So BIP with high probability is insert in LRU position, and with the low probability is insert at the MRU position. So as per the paper, they claim that BIP can handle thrashing. How it can handle thrashing? Because if you have a long trace like this, and it is a repeating behavior like this, but if you have a cache set is small, then if you apply LRU, then everything will be miss. But if you apply this BIP technique, then at least some portion will be in cache, some portion will be in cache, and that's why BIP is better. So the main actual replacement policy, which is called DIP, you can say DIP gives better performance for cache friendly application if we run LRU. So whenever we are running cache friendly application, we can run LRU, and whenever we are running a thrashing application, then BIP will give better performance. So this is fine, but there is a loophole here, and loophole is scanning. If there is a scanning application, then it's difficult for DIP to handle. Suppose the as I think I have explained it in last class also, that it goes with some time, that if at this time period suppose LRU is running, then after some time maybe BIP will start running based on the behavior of the cache. Suppose LRU is running in the cache, so a cache friendly application is running, but sometime it may be possible that in the middle of this cache friendly application, suddenly a scan trace came. So in that case, the LRU policy will not give you good performance. For example, if I there is a trace like this, suppose A1, A2, A3, and then suppose it becomes A1, A2, A3. So it is a cache friendly application, right? It is repeating. But suddenly here, if B1, B2, B3, B20, if you suddenly this type of trace occurs in between A1 and A2, then this is a scanning application. And if this, and at that time, if your underlying replacement policy is LRU in DIP, because DIP is a combination of LRU plus BIP, then if the underlying replacement policy is now LRU, then the entire cache will be the set will be flushed. So this problem cannot be handled by DIP. So if you read this paper that I'll explain today, in this paper they have explained it because DIP proposed in 2007 and RRIP proposed in 2010. So if you are proposing something now, then you have to mention all the existing replacement policy, and you have to discuss it that why it is important to propose a new replacement policy. So imagine in 2010 when these people are proposing RRIP, they should explain at that time that what are the existing replacement policies and why a new replacement policy is required in 2010. In 2007, the DIP is already there. Okay, there are some other replacement policies also proposed before 2010, but I am ignoring those because it's not possible to discuss everything. Why DIP is important here? Because RRIP and DIP are mostly connected. Okay, so I think the main problem of DIP I have explained here, that if it is a thrashing application, then sometimes it's create problem. So now this paper says the replacement policy they say it is RRIP. RRIP means re-reference interval prediction. Re-reference interval prediction means suppose there is a block called A1, it's accessed here, and the block is accessed here again, and suppose there is a block here called A2 and there is a block access here again. So re-reference interval means this is the re-reference interval for A1. It accessed here and it is accessing again here. So this is the re-reference interval for A1 and this is the re-reference interval for A2. So RRIP means if low re-reference interval and a high re-reference interval. So low reference interval means this if A1 is accessing here, and if this block has a low reference interval, it means that it will access in very near future because the reference interval is short. So it will access in very near future. So low means you can consider it as important block, means very near it will be access again. High means if the block has high reference interval means it will access in very distant future. Okay, so these 2 points you have to understand here. What is re-reference interval and which one is better? Low re-reference interval is better in terms of cache property, because this block will access in near future again. And a high re-reference interval means it will access in distance future. But again, here also the term future is added, so you cannot detect it completely, right? So this RRIP, the last letter here, P means prediction. Uh, Re-reference interval prediction based replacement policy. It cannot detect, right? You can only predict that what will be the re-reference interval of a particular block. Okay, so based on this, I'll not explain everything, but I'll recommend you to read this paper once from this section, introduction. I think almost everything mentioned in this paper you will understand. Most of the concept written here are based on LRU, dead blocks, DIP. All this concept you'll understand. So you read the complete section of introduction, and I'll. Oh, hang on here. So when you go to the second page, you'll find this diagram here. So in the diagram is showing different types of access pattern. So this is cache-friendly access pattern that is very easy to understand. This is stretching access pattern. I have already explained what is stretching access pattern. This is actually scanning access pattern that I have also explained. Maybe the notation will be slightly different, but you'll understand it. And there's the mixed access pattern. Mixed access pattern. Just I have shown you example of mixed access pattern. Here you can see the complete thing here. Let me color it. The complete thing is repeating here for n number of times. Okay, and then inside this there is a cache friendly part. This cache friendly part is repeating here a amount of time. Then, and with some probability there may exist a scanning application, a scanning trace here. It's some probability. The CP means probability. So it means that if this part is, if I cut this part, then this is a cache friendly application. But if with some probability, if it arrives here sometime, then it will flush the cache. So this type of application, as I said, is difficult to handle in DIP, especially when the underlying replacement policy is LRU in DIP. So this type of problem will be handled in this in RRIP. So I am not spending time on introduction, but you should read introduction once. I'll advise you to read motivation section also once, because you'll feel these sections are interesting, and I hope you'll understand each and every line here, because these are very easy to understand. See, there are four kind of application that says recency friendly access pattern means cache friendly, crashing access pattern, then streaming means scanning. So these terms are same. Streaming and scanning are same thing. And then mixed access pattern. And then here in this section, they explain that how DIP, see, they have written, explain here DIP, how DIP fails to perform good in mixed access pattern. And you can see a graph also here. They have shown a graph in their motivation section, then how DIP fails to perform good in if the application is a mixed access, have mixed access pattern. So that's why they at the end of this section here, they have explained, they mentioned that why they have motivated to propose a new replacement policy. Why? Because this there are some problem with DIP cannot handle everything. So after this, maybe you can skip this related work section. It is not important for here. But if you read related work section, then you will realize that what are the other replacement policy proposed before 2010. So they have discussed all these things. So with this, we'll directly start with the replacement policy, RRIP. So before understanding the replacement policy, RRIP, will try to understand another replacement policy that is called, it is written here, right? It is called NRU, not recently used replacement policy. Okay, so I think it will be easy to explain from, I don't know, it is sometime it is, okay. First we'll try to understand LRU, and then we'll understand this is here. The first column is for LRU, second column is for NRU, not recently used, and last column is for SRRIP. There are three proposal in this paper, though it is called RRIP. First proposal is called SRRIP, then second proposal is called DRRIP, and then there is third proposal called TADRRIP. So it is almost similar as DIP. So first, let us try to understand LRU, because if we understand LRU, then only we'll understand the other concepts here. So what they did here, you can see there is a trace they are using here: A1, A2, A2, A1, then B1, B2, B3, B4, then A1, A2 again. So this is the trace, and you can see from this trace, this B1, B2, B3, B4, you can consider this part as scanning part. Okay, this is they are using a trace here, and they'll show that how many misses and hits can be observed if we go for LRU, if we go for NRU replacement policy. So first we will discuss here an LRU. So I think the better way to understand is like this. Okay, just concentrate on this column, LRU column, and ignore these two column. NRU and SRRIP is not required. Is it visible? First row here, four I's are written. Is visible from the last row? Okay. So see, initially the cache is empty. As I said, I am only targeting one set. So initially the set is empty and the request is for A1. So if the request is for A1, cache is empty, then I can place A1 in the first position. And here it is written wrong. It is RRIP head, means you can consider this is actually MRU position, and this is actually RRIP tail, means this is actually LRU position. Okay. So now what we will do, we'll place A1 in place of I, right? In place of MRU position. So, and it will be a miss, right? It is a miss. So this is the current status here. Once you place this A1 here, then now A1 is here in MRU position, and remaining three are I. So in this moment, if there is a new request called A2, so if there is a new request called A2, again there will be a miss here, right? Because A2 is not in the cache. It will be a miss in the cache, and then we have to after this A2, the status of this set will be A2 A1. Why? Because A2 we have to insert in the MRU position, right? So if I scroll down it, see, it is A2 A1, right? So in A2 A1, again the next request is again A2 here. See, the next request here is again A2. So if the next request is again A2 here, then there will be a hit in the cache, so it is written hit here. So it is a hit in the cache. So so nothing will change after this line. So after this line also A2 A1 will be there, I think. See, A2, and nothing is changed, because according to promotion policy, if there is a hit, then we have to promote it in MRU, but in that case A2 is already in MRU position. So now this is the sin, A2 A1 in the set, and the core is requesting for A1. So in this case again there will be hit, right? So there will be hit, and now according to promotion policy, we have to promote A1 in the MRU position. So the after this line, the sequence will be A1, A2, A1, A2, II. So if I go down, see, it is A1, A2, II. Okay, now it is requesting for B1. When it will request for B1, B1 is not here, so there will be a miss. And now the sequence will be B1, A1, A2, 1I. This will be the sequence. So if I go down, see, B1, A1, A2, I. So now in this case, in this moment, if code request for B2, then again there will be a miss here, and now the sequence will be B2, B1, A1, A2. B2, B1, A1, A2. Now this set is full, right? This set is full. Now at this moment, if it is requesting for B3, then which one should we remove? A2 will remove. So it will be B3, B2, B1, A1. B3, B2, B1, A1. Now again, if it is requesting for B4, then there will be miss again. I'm not explaining everything one by you will understand all other points. So at the end here, when it is requesting for A2, this is the content A1, A4, A1, B4, B3, B2. So obviously A2 will be miss here. So we have to remove B2, and the content will be A2, A1, B4, B3. So this is the final content. I think, yeah, this is the final content. So if you just follow this column, LRU column, then how many number of there are only two hits, right? There are only two hits. Remaining all are miss. So they are using a specific pattern. You have to observe the trace here. Trace is this. So A1, A2, A2, A1, and after this there is a small scanning trace in between. Okay. So now let us see how NRU will handle it. So NRU has a very interesting technique. If we remember, in last class I said, if you have a four-way set associative cache and you want to maintain LRU, then you need 2 bit for each, right? 1 means LRU, maybe 0 0 you can say MRU. So here they're saying no, they will use only 1 bit, no matter how many associativity is there. 0 means it's a recent block, and 1 means it's a old block. It doesn't mean that it's a older, so they'll just say old. So 1 means it's a old block, so you can remove it. 0 means it's a recent block. So this is the only two category here, old and recent. So there may be multiple old blocks, it's possible. So in that case, they will choose one among all the old blocks. So that's why you can say initially, if I move it here, initially see that now we are concentrating on second column. Ignore the first column, just concentrate on the this sequence A1 and the second column. So initially set is empty, I, everything is empty, and the values will be 111 in all the positions. Okay, just one bit here. So now when we'll request for A1, so here we'll insert A1 in the first position here, A1, and we'll assign a value to 0 here because it's a recent block. 0 means recent. So you are just inserting the block in the cache. So you have to make this block as 0. So obviously the first it is miss, and then you will put it in this position and you'll assign 0. So if you go down, see it is A1 0. A1 0, right? So in this moment, if you go for A2, then again A2 is a miss here. So first there I have written miss here, and then we'll assign A2 here. Any here the recency MRU position, LRU position is not important. So I think I can put A2 here also, A2 0. So this is also fine, I think. Yeah, see A1 0, A2 0, and there are two more space still empty. So now if it is request for A2, then we'll simply return A2 and nothing will change because 0 means recent. So see, nothing is changed here. Now it is requesting for A1. For A1 also nothing will change because there is a hit and it is already 0. 0 means recent block, so nothing will change. So if I go to next line, nothing will change. Now it is requesting for B1. So when it will request for B1, then there is empty space already available here. So B1 will be inserted here. And if I go down, see B1 is the same way now it will request for B2. So B2 will be inserted here. And now this is the point here, the set is full, right? The set is full. Now it is requesting for B3. So if it is requesting for B3, now the replacement policy will actually start working from this point. Before this point, there was no use of replacement policy. There was free space in cache, right? Now there is no free space in cache. So now to place B3, I have to remove one of them. So according to their policy, they say is that remove old blocks. But here you can see every block has 0 mark, right? So it means all are a recent block. So in that case, their policy say they increment the value of all the blocks. So all the this will become 1 1 1 1. Increment the values of all the blocks and then choose the leftmost block. So in this case, which block will choose? We'll remove this A1, and in place of A1 we'll place B3 and we mark it as 0, right? So B3 and then A2 1, B1 1, and B2 1 will be the next. So if I go here, see B3 0, then A2 1, B1 1, B2 1. Okay, so in this case, again, if core is requesting for B4, then again there is no space, but obviously there are 3 old blocks now, right? So 3 old blocks means we'll choose the first one. First one is A2. So we'll choose A2, and in place of A2, we'll place B4 0. See, in place of A2, now it is B4, and now we'll mark it 0. So now it is now it's a turn for A1. So A1 is not here. So again there will be miss, but there are two eviction candidates. The 2 old blocks are already there, B1 and B2. So I'll remove B1, and in place of B1 I'll place A1. See, A1 is placed in place of B1. So now if it is requesting for A2 here, then still there are one old candidate. This is called B2. So we'll replace B2, and in this case they'll store A2. So this is called NRU. So see, there is no difference between LRU and MRU. Number of misses, number of hits are same. So why I have explained NRU? Because it will help you to understand the SRRIP, or that's why I have explained. Otherwise, you can see there is no difference. The way they have they have taken this example. Maybe for other example, you may face difference between LRU and MRU, but for this particular example here, there is no difference. Now, with this knowledge, let us try to understand SRRIP. As I said, before going to discuss SRRIP, I'll quickly explain the complete summary of this paper. They are saying the paper name is RRIP. In this paper, they have first proposed a replacement policy called SRRIP, that is called static RRIP. Then they have explained the same paper, the same way. Then they have explained a concept called BRRIP. I hope you are understanding. It's same as BIP. And they explained a concept called DRRIP, which is a combination of these two. This is SRRIP plus BRRIP. Exactly same as the last paper that I've explained. So this is, so SRRIP is their first proposal. You can consider DRRIP is their second proposal, because BRRIP is not independently used, right? It is always used inside the DRRIP. So SRRIP, DRRIP, there are two proposals. And the third proposal is for if there are multiple codes and there are multiple applications, then the third proposal is called TADRRIP, which I think I have given uploaded an extra lecture for TADIP, right? So for DIP paper, there is the extension for multi-threaded, but here in this paper, SRRIP, DRRIP, and TADRIP, there are three proposals. But for you, I think DRRIP is not important. You can ignore that also, but you should understand what is SRRIP and what is DRRIP. Okay. So the next point is this to understand SRIP, I think re-reference interval is I have already explained. So they predict the re-reference interval, and a block which is low re-reference interval, they will try to retain it in the cache. And the block which is high re-reference interval, they will try to evict that block from the cache. This is their point. So for this, they are using one more value that is called RRPV, re-reference prediction value, I think. Re-reference prediction value, RRPV. And this is a counter, so they use m bits for it. So if there is m bits for it, then to insert a block, the insertion policy means, so m bits means what happened if in NRU policy you have only one bits, right? And in NRU I said there is only one bit. In SRRP there will be m bits for each block. This is the only difference in NRU. That's why NRU is important to understand. In NRU, there is only one bit for each block. Here, there is m bits. And when they insert a block in now I am explaining SRRIP. Every replacement policy has insertion, right? So insertion policy, they said insert in 2 to the power m minus 2 position. So every time, if you remember in NRU, when we are inserting, we are assigning 0, right? So they will assign a value to the power m minus 2. So this is their insertion policy. Then their promotion policy is 0. They'll directly promote it to 0. And I hope you are understanding 0 means very important block, right? It is by m bits, they are representing RRPV value. Basically the re-reference interval prediction. So if it is 0 means the low, right? And at the beginning I said low means very important block. This block will be referenced in very near future. So 0 means very important block, or you can relate it with MRU also. So the moment I say a promotion policy 0 means it is same as LRU, right? In promotion, LRU also we promote it to MRU position. So promotion policy is 0. And then eviction policy. In eviction, they evict from 2 to the power m minus 2 to the power m minus 1, this position. From this position, they evict. So suppose if the m bit is 2, so your m bit is 2, then insertion will be at position 2, promotion will be 0, and eviction from position 3. Isn't it? So when we'll try to evict, we'll check that which are the blocks having RRPV value 3. From these values, from this block, we'll choose 1. This is the eviction policy. Promotion policy means if there is a hit in the cache, we'll change the value to 0. Okay. And insertion means every time when we'll insert a new block, we'll insert it in the with the value 2. So now with this knowledge, let us try to understand the last column. Why I'm removing it, because I want to keep this board white to understand this diagram. Okay. Last column, SRRIP. Everything is empty, and initially everything will be 333. Same as in NRU, everything was 111, right? Here it will be 333. Why it is 333? Because they assume m bit here as 2 bit. Okay. So that's why it is 2 to the power m minus 1 is 3. Now when A1 will be, A1 is requesting by code, so the trace will be A1, 2, and then III, right? Because insertion means we will insert at the second with RRPV value 2. See, A1, 2, III. Now it is requesting for A2. So again, A2 there will be miss. Obviously there will be miss, but we'll insert A2 here with again value 2. Value 2. Now for A2 there will be a hit here, right? So there will be hit. So if there is a hit, then promotion policy will apply. And promotion policy means the A2 should become A2 0, right? So if I go next, see, A1 is 2, but A2 becomes 0 because of promotion policy. Now it is requesting for A1, so according to promotion policy, A1 will be also 0. This A1 0, A2 0, fine, easy to understand. I think next is it is requesting for B1, then just B1 2 will be here, and it is also easy to understand. B1 2. Next it is requesting for B2, so there will be B2 2 here. So now the set is full. A1 A2 are 0 0, means they are important block, right? And there are two more blocks here, B1 and B2, having 2 2. So now the set is full. Now it is requesting for B3. So what to do? I said eviction policy means evict from those block who have the RRPB value 3. But if you see the set, there is no block having RRPB value 3. So in this case, we'll just increment all the values. So if we increment all the values, let me write this set here. The set is saying A10, A20, B12, and B22. So if I increment, it will be 1, 1, 3, 3. After this, which one will be the eviction victim? V1 will be the victim. The block which we normally remove in replacement policy is called victim block. So B1 is the victim block because there are two blocks here having 3, 3, B1 and B2. In this case, they always choose from the left side. So B1 will be the victim block. So we'll remove B1. In place of B1, we'll store B3 here with RRPB value 2. So the next line should be here A1 1, A2 1, B3 2, and B2 3. See, A1 1, A2 1, B3 2, and B2 3. In this case, if there is a request for B4, then which one will remove now? B2, because it is already marked as 3, right? So we don't need to increment. Simply we'll remove B2, and in place of B2, B4 will be placed, and value will be 2. Now for A1, if we request for A1, see now there is a hit in A1. If we go for A1, there will be a hit in A1, and now the value of A1 will be A1 0. And now for A2 also there will be a hit here, and the value of next value will be A2 0. So that's it. Now you can see the difference. You can see there are two hits at the lower end, right? For A1 and A2, you are getting two hits in SRRIP. This is not the case for LRU. This is not the case for NRU. So this is how SRRIP is different from LRU and MRU. First, forgot about the difference. First question is, did you understand SRRIP? Insertion, promotion, eviction is clear, right? First understand SRRIP, then we will try to understand the difference. If we understand SRRIP, then when you try to understand difference, you can see there are two more hits here, two additional hits. So it means that the SRRIP is more scan resistant, because you can see the trace that we are using A1, A2, A2, A1, and then A1, A2. If I ignore the intermediate scan part, so it has some temporal behavior, right? It's not completely tracing, it's not completely scanning. Tracing means A1 is using here. If A1 is using here, then A1 will not use for a long time. After a long time, again it will use, right? That is called tracing. It is not the case here. See, A1 is repeating very small duration. Same case for A2 also. So it has temporal behavior also. But in between this temporal behavior, there is a scanning application, and that scanning can completely degrade the performance of LRU. But that is not the case in SRRIP. In SRRIP, those scanning block can be handled. So this is just an example, and if you read the book, you'll understand that this how much what is the strength of this SRR, means how much scanning it can handle. What about if instead of B1, B2, B3, B4, if I write no, there are B5, B6, B7, B8 is also there, and then I'll call for A1 and A2. So if the scanning application instead of this length, if your scanning trace is of this much length, then how SRRIP can handle it. That depends on the M bit value. If your M bit is high, it can handle. If M bit is low, it cannot handle. But if we go for very high M bit values, then there will be hardware overheads, right? So there should be a balance between this. So in this paper, I think they said that there is a formula also for this here. So I think the ideal mbit value they said is I think based on the associativity. So if your associativity is 16, then maybe 5 will be better. Because 16 to represent 16 you need 4 bits, so there's 5 will be better. If your associativity is 8, then they said 4 will be better RRPB value, because you cannot go for a larger RRPB value. because another point is when you are saying about scanning application and all. So all the application they run here, I think last class also I have shown you some benchmark, right? If I scroll up and I show the first diagram, see, if you see the x-axis of this diagram, there are these are all benchmarks, right? So these are benchmark applications, and normally benchmark applications are there may be some scanning application, there may be some mixed applications, but those are real applications. So that's why I think in one of my lecture I have given you I use a term called security, right? So security means till I think 2015, whatever replacement policy, whatever improvements done in computer architecture, we assume that the world is innocent, or we assume that if Intel will design a processor, if Intel is setting a replacement policy like RRIP, no one will know about it. That we assume, but that is not true, right? It is very easy to know, understand. Even an employee can leak it, that what are the underlying replacement policies going on. So that's why there is a new research area is nowadays is very important in computer architecture. It's called hardware security. Means in 2010 when they proposed this policy RRIP, they never thought about this, that okay, किसी ने जानबूझ के एक application बनाया जिसका trace बहुत बड़ा है, scanning. So how it will handle, they didn't understand this. They just explained that okay,
all the existing benchmark policies जो है, benchmark application, see, for all the benchmark application it is handling properly. So there is one way that if you are proposing a new replacement policy, first thing is just try to compare with benchmark policies. That is fine. But if you want to think a different way, and if you want to attack this policy, then maybe you can first implement RRIP. I think you don't need to implement RRIP. Chances may RRIP implemented. Maybe you can try to develop an application which is longer scanning application, and then try to understand that how it is behaved. So obviously all the results that's shown in the research paper, they say no, on average scanning का length कितना होता है, it's on average, right? Because they are assuming it for all the innocent applications from benchmark. But if someone is the attacker intentionally try to create a longer scan trace, then I think RRIP will not give good performance. So those are called DOS attack, denial of service attack, and this is a big area of research. I cannot explain it here. In fact, now in CSE department there is elective course going on hardware security, memory security. But at least you should know some basic thing from here that it is possible to adopt this type of replacement policy. But till 2015, no one think in this direction. So we will also not think because we are in 2010 now.
yeah, because this paper that I'm explaining is from 2010. Okay, so I hope SRRIP is clear. Okay, so SRRIP clear हो गया तो बाकी और कुछ है नहीं इस पेपर में. Why I'm saying बाकी और कुछ है नहीं, because if you understood last lecture, then after SRRIP remaining things are just inspired from the DIP paper. Okay, if you understood SRRIP, then I said SRRIP, that is static why it is called S is for static, because here the insertion policy is again static. We are not dynamically changing the value, right? It is every time 2 to the power m-2 insertion policy. Some more points here, why they are inserting it 2 to the power m-2. So if this is your set, so if you remember, if we say this is my LRU position and this is my MRU position, so and MRU position you can consider as suppose low SRRIP, na? Low RRPB. As I said, na? MRU means RRPB 0 means MRU, we can assume, and it is high RRPB. So where they are inserting every time in this position, right? RRPB value high -1 कर रहा है ना, so high is 2 to the power m-1, so 2 to the power m-2 पे insert हो रहा है, means every time they are inserting here. So it means that if you try to relate it to the LRU, that every time whenever they are inserting new block, they are not putting it in LRU, they are not putting it in MRU, they are putting it in just one position before LRU, and they are waiting, assuming that if this block is an important block, then in near future definitely there will be one more request, and if there is one more request, then we will promote it to MRU position. This is their promotion policy, right? And if it is not requesting in near future, then they're assuming that this block has no temporal behavior. This is only for streaming. So let it remove. So very soon it will remove, because if you try to ignore the RRIP part, if you just try to relate it to the LRU, then also it will remove very quickly, because ये LRU के just equation आगे अपने insert किया. So this is how they are working. And one more point, when you will see it, I think there is, I think one point here is SRRIP HP बोल के कोई term मिलेगा आपको शायद. Let me see. Uh, SRRIP, see RRIP FP or RRIP HP, दो मिलेगा, HP and FP. So the difference is here in promotion. One that I am saying is HP. HP means promotion means hit हुआ तो direct zero. Okay, and in FP means sequentially promote. If currently the value is 3, then hit means it will decrement the value to 2. Then next state you will decrement the value to 1. Next, so gradually you will promote it from LRU to MRU. So that is called FP, SRRIP FP. But most of the experiments they shown here are for HP. So and the example here is also for HP, right? Promotion means direct 0. Okay, so if you understood SRRIP, then maybe you are also understanding the limitation of SRRIP. SRRIP is scan resistant, that is fine. And I said the limitation here also, the when it will not be scan resistant, that I've also explained. But yes, if your M bit value is enough, then it is it's some extent it's scan resistant, but it is not tracing resistant. Again, if you have a block A1 here, and there is a long trace here, and after this trace you are repeating this A1 here, then this SRRIP cannot hold A1 for this, right? Scan resistant, fine. SRRIP is scan resistant, but it's not thrashing resistant. So that's the point here. If you go to this paper and if you start reading from 4.3, then you can see first line, SRRIP utilize the cache when the re-reference interval of all the larger than the available cache. Re-reference interval cache size it means thrashing. So it means SRRIP is not for thrashing. So what to do for thrashing? So they say the same thing. They are going for bi-model RRIP. And bi-model RRIP, if you read here, then it is saying that it insert majority of the cache block with the distance reference interval. Distance means 2 to the power m-1. Okay, and infrequent in the new cache block with a long reference interval to the power m-1. So what they are saying that with high probability they will insert in 2 to the power 2 to the power m-1, and with low probability they will insert m-2. So 2 to the power m-2 was the case for SRRIP, right? So now they are saying this is their BRRIP, and in BRRIP with high probability they will go with this position of insertion. That means inserting in LRU position, right? If you compare it with LRU, and this is with low probability they will go with 2 to the power m-2. This is their BRRIP policy. And again, they say the same thing here. If you go for BRRIP, if you BRRIP in your cache, then cache friendly application will drastically performance. So that's why they're saying only BRRIP is not a solution. So let us combine. So how to combine? So the same thing. They say it is DRRIP and DRRIP, and it's a combination of SRRIP plus BRRIP. And how to choose between these two? Again, set dwelling that I've explained in last class. So they will use set dwelling. Based on set dwelling, they'll decide whether we'll go for SRRIP or whether DIP. Now, if I write here the DIP, I have explained in last class, DIP was LRU plus BIP. So if I consider BRRIP and BIP, both are tracing resistant, right? So the advantage here from SRRIP, because LRU is not scan resistant. LRU is not for scan resistant, but SRRIP is scan resistant. So DRRIP is a scan resistant as well as scan resistance. Scan and thrashing, both it can resist in some extent. So in this way, DRRIP is a better DIP. But if the way these two papers are written, you will find a lot of similarities, because BRIP is also similar. Then how in DRIP selecting between SRRIP and BIP based on set dwelling, all are similar. So if I go back to this slide here, see, if you read the next section, next paragraph here, means this paragraph, then you will find all this concept. We propose dynamic reference interval. We propose dynamic reference RRIP that use set dwelling. I hope I have already explained set dwelling. Set to identify which replacement policy the best suited for the application. So it is same. Say set dwelling monitor they will use. So set dwelling monitor we have used already in two papers, in cache partitioning paper and in DIP papers, right? So again in this paper also they are using set dwelling. So that's it. That is DRRIP. And after DRRIP, here there is a section for 4.4. Here they are comparing their how SRRIP is better than LRU. So I've already said LRU cannot resist scan. It can resist scan, but I think the what scan is not available in this paper. They are using stream. So scan and stream are same thing. And then this is our 4.5 is RRIP extension. That is for if there are multiple applications. Instead of one core, you have multiple cores, and multiple cores are running different application. And in one of these application is scan. So उस time पे क्या होगा? So in that case they said no. So they are assuming that each application has a thread. Okay, so they say thread aware dynamic thread aware DRRIP. That is called TADRRIP. So for this course, TADRRIP is not important. The same I say TADIP is also not important. So if you are interested, you can read this TADRIP also, because obviously the simulator that I have given ChamSim, in ChamSim you can simulate both single core and multi-core, right? So if you want to run multi-core, then there will be very interesting that if you are underlying replacement policy DRRIP, then try to run a scanning application in one core. Give one trace for scanning trace and one trace and a cache-friendly trace in ChamSim and see how DRRIP is degrading the performance. And then maybe you try to implement TADRRIP. I'm not sure about TADRRIP is implemented in ChamSim or not, but SRRIP and DRRIP are implemented. You just need to change the parameter. Okay, then you can check that how DRRIP is giving benefits or not. Okay, so this is actually a big area that this is called if one application is stressing other application, then how to handle. So far, I am not discussing all these things. I'm making it simple. I'm assuming that there is only one code, and based on the behavior of only one trace, I have explained DIP and DRRIP, right? So maybe if time permits, I'll go for other replacement policies also. So here I'll stop, but before stopping, as I said, the paper is from 2010. So if I again come back to 2020, then there is another important point is if somehow a attacker can know which are the sample sets, then what he can do. Normally, sample set may be random, okay, but if it is random also, and most of the time what happens that they at the when the computer will start at the beginning, when the computer will boot at that time they randomly select few set for sample set. But if normally servers run for years, right, we don't normally shut down it. So once the sample set are decided, they will remain same. So there are some research recently on 2017 or something that it is possible to do some reverse engineering and find out which are the sample sets. So imagine that if some attacker knows which are the sample sets, then it is very easy for him to fool the entire case that okay, no, go for LRU. What it will do, it will just create a small trace targeting only those sets, sample set, and उसमें बहुत ज़्यादा miss कराएगा, isn't it? If you want to go for LRU, and if you want to go for MI, it means if you go for this other part, VIP suppose, then it will create more misses in LRU part. So it can force to follow the entire case with a replacement policy which may not be suited. Why? Because every case behavior is depend on those sample sets, right? And we already know how blocks map to a set based on set index. So attacker क्या करेगा सबसे पहले malloc use करेगा. It's very easy in C program. It will use a malloc and reserve a huge address space. बड़ा address space दे दिया, and you know the base address also, right? Malloc से बड़ा address space reserve करेगा, you know the base address. So sequentially one by one it will start all the address and find out which are the addresses mapping to that particular set. Address तो होगा ना, is it will find out which are the addresses mapping to that particular set based on that particular set index, and उसका list बनाएगा, and then it will only send those blocks, and those blocks will keep flooding that sample set, and उसके basis पे sample set change हो जाए, sample set will say no, go for LRU. Maybe LRU is not a best policy for every set, but it can force. As I said, these type of concepts are not discussed even 2015. I think the concept that I am saying now, it is not proposed yet also. Maybe I'm not sure. Maybe you can try also this type of thing. So that's why if you want to, not necessary for this course, not necessary for this project also,
But if you want to do further research in this area, you can keep thinking as security is a very important point here. Means every time you read a new paper on architecture like replacement policy, pre-fetching, cache coherence, you can think in this direction also. Is it possible to misuse it? Because as I said, when people propose them, they don't think in this direction that someone will misuse it. Okay, so I'll stop here. If you have any questions, then you can ask. And in the meantime, let me check if I have any online questions. There is no online questions. So if you have any question, you can ask. Any questions?
Sir, which one is better among BIP and BRRIP for thrashing?
BIP and BRRIP, I think BRRIP is it will be slightly better. Why? Because BRRIP means what? It's a combination. It is either inserting in 2 or in either three, right? And in if I go with BIP, then it is inserting in LRU or MRU. So it is either 3 or 0. So I think BRRIP will give slightly better improvement. A slight better improvement it should be BRRIP. But again, many things depend on application period also. The results they are showing here, these are from 2010, right? And now the computer needs different types of data. Now in this 10 year, you understood, you may know that how big data things boom, right? And now everyone knows what is big data. In 2010, I think if 250 GB hard disk was enough. Now you know a 2 terabyte hard disk is also sometimes not enough. Even for small assignment also, maybe some teachers will give you some data which will be in GBs, right? And terabytes. So now the application behavior are changing every day. So maybe the based on which property these authors are claiming something on 2010 may not be true in 2020. So that's why every time the people are trying to choose new, try to propose new replacement policies. But yes, optimal is still optimal. That I say, optimal is still optimal, and there is still a huge gap between the optimal and all the replacement policy that is possible to implement. And the two papers that my student will explain you, Hawkeye and Mockingjay, what they try to do, they try to simulate the behavior of optimal replacement policy. And they say that their policy is much closer to optimal replacement policy. And again, there are also interesting short limitations are there, but I will not explain it now. Let us first understand this two replacement policy, then I will explain that what are the possible limitations, but those will not be a part of this course. I'll always try to give limited syllabus for exam as well as a project. And maybe I'll discuss many other things, but don't think that all are as a course load. कोर्स लोड में जो भी होगा मैं स्पेसिफिकली बोल दूंगा दिस इज कोर्स लोड एंड दिस इज आउटसाइड कोर्स लोड ओके सो दिस इज PADLRP is not your course load in your course load if you are interested you can it okay any other questions if there is no question then we'll stop here maybe we'll again make tomorrow